S-Chan presents educational video lectures as per the AICTE curriculum. Difficult concepts made easy. Study anywhere, anytime.
Have you heard about the terms inertial and non-inertial frames of references? In this video, we will be discussing the same topic.
If you want to study this topic in detail, refer to the book by S-Chan Publishing. Link is provided in the description box.
Hello everyone, I am Anmol Bhatia and welcome to S-Chan Academy. In today's video, we will be learning about the inertial and non-inertial frames of references. So in this video, we will be discussing about these topics, and these topics are non-inertial frames of references, the rotating frame of references, and Foucault's pendulum. So let us start with the topic. So before coming to the non-inertial frame of reference, which is also linked with the pseudo forces, we will be discussing about the frames of references initially. So let us consider an example in which a man is standing stationary and there is a vehicle in which two persons are sitting. One person is termed as A and another person is termed as B. This person is termed as C. So if we talk about the car is in motion and it is moving with a velocity V. If I ask this person that what about the person A? So this person will say that this person A is in motion or rest. So this person A would be at rest and this person B would be at rest as far as the perception from A and B is concerned. But if we ask this person C that tell me about the motion of these two, so that person will definitely say that these two are in motion. So whose frame of reference is generally acceptable? So here the frame of reference is basically, it comprises of the group of physical reference points and abstract coordinate system that will help to standardize the calculations within the given frames. So what is that coordinate system associated with these bodies? So these are the coordinate systems. Let's say this man is standing at this point, which is origin, and this is the frame of reference, which is X, Y and Z. And similarly, the frame of reference for this car would be X dash, Y dash and Z dash. So the frame of reference, as I have told you, that it is particularly the coordinate system which is associated with a particular body, and that is helpful in calculating the positions of a particular body with respect to some other body. Now, coming to the frame of references that I have just elaborated. Let's say we have a frame of reference S and that is having the axis values as X, Y and Z. Now let us say that the car is moving and that car is moving to another frame of reference, which is S dash, and that particular S dash is having these coordinates, which is X dash, Y dash and Z dash. So we have two different frames of references. So before coming to the non-inertial frame of references, let us understand what is inertial frame of reference. So an inertial frame of reference is that particular frame of reference in which this Newton's law of motion holds true. That means there is no external force that would be acting on a body and it would stay at rest or in the uniform motion. That means we have a velocity which is constant. So here we have a constant velocity and we don't have any external force which is acting on the body. So this is particularly linked, or this particular situation is called as inertial frame of reference. Now the non-inertial frame of reference, considering the similar example, in the non-inertial frame of reference, the Newton's law of motion is not true. Here particularly what happens, if this is a particular frame of reference which is termed as S and that another body is moving with a velocity, let's say a car is moving with a particular velocity, but here we have that velocity to be constant. Now, if this velocity is constant, then the acceleration would be 0. So, if in any case, if the acceleration of a body with respect to another body is 0, then we name it as a non-inertial frame of reference. Otherwise, if the velocity is not constant, we will say that it is an inertial frame of reference. So, a non-inertial frame of reference would be having a situation in which it has a constant acceleration, whereas in the inertial frame of reference, the acceleration of the body is termed as 0. So, if you have a constant velocity, then the acceleration is 0. The frame of reference is called as an inertial frame of reference, whereas if the acceleration is constant, then the frame of reference is called as a non-inertial frame of reference. Let's say in order to understand this non-inertial frame of reference, we consider an example. Let's say this is Earth and a person is standing at particular location and that person is watching this particle. So, this particle is moving with a constant velocity. If the particle is moving with a constant velocity, then with respect to this man, this frame of reference would be inertial frame of reference, because this particle is moving with a constant velocity. In the similar fashion, the acceleration of that body or the particle is 0. Now, if the acceleration of the particle is 0, then we term it as an inertial frame of reference. Let's say we have another situation in which the man is placed or the man is standing on moon and that man is watching this particle from moon and the particle is at Earth. So, what happens? The position of this particle is with respect to the Earth and that particle is accelerating with respect to Earth. So, that means it has some value of acceleration and that acceleration value is constant. So, we name or we term this frame of reference as a non-inertial frame of reference. So, what is it? A non-inertial frame of reference is that frame of reference which is accelerated with respect to the assumed inertial frame of reference. And here, as I have mentioned, that the Newton's law will not hold true in these frames. I have given you an example of this Earth and Moon situation. So, if we assume that Earth to be an inertial frame of reference, then the Moon becomes the non-inertial frame of reference, as it is having the accelerated motion with respect to the Earth. Now, if in a particular situation or forcefully if we want Newton's law to be true in the non-inertial frame of references, then what needs to be done? So, in that particular situation, we need to have a force which is called as a pseudo force that I have mentioned in the initial part of this lecture. So, I have told you that if we want to make this Newton's law hold true here, so we need to have some mysterious forces that needs to be acted on the particular particle or on the particular surface. So, that particular force is called as a pseudo force, right? So, the laws of motion as would be same in case of the inertial frames and also in case of a non-inertial frames. And in classical mechanics, we particularly explain this motion of the body in non-inertial frames of references by introducing a fictitious force, or you can say the pseudo force, or any mysterious forces. So, any mysterious force which is acted on a particle, but that mysterious force is there on the particle just to have this Newton's law of motion holds true. In that particular situation, we name it as a pseudo force. Now, what does this pseudo force exactly means? So, let's say we consider the same situation in which the man is standing and the man is standing in a particular frame of reference. Let's say the frame of reference is S. And the car is moving with respect to this man and the car is moving with a constant acceleration. So, as I have demonstrated in the diagram that the car is moving with a constant acceleration and that car is situated or placed in a particular frame of reference which is X dash, Y dash and Z dash, and I name this frame of reference as S dash. So, if we look at that situation in which the man is watching the car, so at that particular situation the acceleration is constant and that would be in the positive direction. But if a person is sitting in the car, looks at the man, so that person would feel like that the man is going behind. That means the acceleration is negative in that particular situation. So, here the acceleration is negative, that means the force exerted would be F equals to minus m into a, because force is mass multiplied by acceleration. So that would be the negative value of this force. But that force is a mysterious force or a fictitious force. This is not exactly exerted on the body. So that's why we name it as a pseudo force, and the pseudo force is particularly there in case of a non-inertial frames if we want to hold this Newton's law of motion as true. So defining the pseudo force which does not really act on the particle but appears to be acting on the particle, and that is due to the acceleration of the frame, and that particular force is called as fictitious force or the pseudo force. So example of the non-inertial frame of reference basically that we will be talking in the later slides would be the rotating frame of references that we will be discussing in the forthcoming slides. So talking about this rotating frames of references, let's say the biggest example of this rotating frame of reference is Earth. So as you can see in the diagram that the Earth is rotating and the frame of reference made on the surface is X, Y and Z. Let's say on the surface of Earth is X, Y and Z. Now if this Earth is rotating, that means this frame of references are also rotating with respect to the Earth. So this is the situation or the special case of a non-inertial frame of reference in which we say that this frame is also rotating with respect to some inertial frame of references. Here we will be deriving this expression, and this expression would be mass multiplied by this acceleration, then twice of m omega Vn minus omega cross r. This expression we will be deriving, and here as we know that the Earth rotates about its axis in 24 hours, therefore it has a fixed time frame, so that it rotates with a particular frame of reference, and that particular frame of reference is known as a non-inertial frame of reference. So this particular situation is to be explained now. In the previous situation, I have told you that these are the fixed values of the coordinates, which is x, y and z. Now I have told you that these the Earth is moving or Earth is rotating, so the frame of reference would also be rotating in this situation. So x would be shifted to x dash and y would be shifted to y dash. One axis would be fixed so as to get the object in rotational motion. So this would be the condition, or this would be the situation of rotating frames of reference. We stop here for a short break, and after coming back from the break we will be deriving the expression for the rotational frame of reference.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome back after the break. Before going to the break, we have learned about the concepts of inertial and non-inertial frames of references. Also, we had a discussion on rotating frames of references, and I have told you that we will be deriving an expression of the rotating frames of references. So, without wasting much time, let us start with the derivation. So, the derivation that I am talking about is this derivation, which is particularly related to rotating frames of references, and the example of this rotating frame of reference is the Earth. I have told you that the Earth is rotating about its axis, and so as the frame of reference is also rotating with respect to a fixed or a stationary point. So herein we have an example of a coordinate system in which we have this coordinate system x, y and z, which is depicted by this red line. And I have told you that if this Earth is rotating, so the frame of reference is also rotating, and herein this z axis is fixed, and about this z axis this frame is rotating. So this x changes to x dash, y changes to y dash. So considering two frames of references here, one frame of reference is termed as S and the coordinate values are represented as xi, yi and zi. These indicates the inertial frames of references. And the next frame of reference would be S dash. That would be the rotational frame of reference or the rotating frame of reference, in which the axis values are denoted by xr, yr and zr. And it also has an angular velocity which is relative to the initial frame of reference. Here these red indicates the initial or the inertial frame of references. This is xi, yi and zi, and after rotation this becomes xr, yr and z is fixed. So zi and zr are at the particular fixed position. So we have a fixed point here which is denoted by this colored line, and it has a magnitude which is r. So talking about these position vector, so the position vector here is termed as p, and we have this r which is the magnitude of the position vector with respect to the particular frame. So here for the magnitude for the inertial frame of reference, that would be equal to the magnitude of the rotating frame of reference, and that is termed as r. Both of them are equal because the origin is coincident. Now if we want the particle to be stationary, or if we assume that the particle is stationary, then the observer in the rotating frame of reference will see the particle moving with a linear velocity. So if the observer is there in the rotating frame, so that observer will see the particle moving with the velocity, and that velocity is termed as minus omega multiplied by r, where r is the magnitude and omega is the angular velocity of the body. So this expression, which is velocity of this particle with the rotating frame of reference, that would be equal to the velocity of the particle at the inertial frame of reference minus omega into r. So omega into r is that velocity which the observer in the rotating frame would see the particle, and that particle would be having this linear velocity. So here what happens, this expression we got, and from this expression, if we want to find out what is the value of this inertial frame of references distance, so that would be, this remains here and this omega multiplied by r goes into the left side of this expression. So it would become dr by dt of r at that particular part for rotating frame of reference, and plus omega into r. So I can write this as velocity for the initial frame of reference. I can write this part as the velocity for the rotating frame of reference, and this remains the same part. So we will get two expressions. One is this expression, which would be a standardized expression for the rotating frame of reference, and another expression would be this expression, which is the second expression. This would also be a standardized expression in terms of distances. So x here is the distance, and dx by dt indicates the rate of change of distance, that would be velocity component. So this is the velocity component for the inertial frame of reference, velocity component for the rotating frame of reference, and this part would be the angular velocity multiplied by the distance, or you can say that this would also be r. Coming back to that expression, which is this expression, which is vi equals to vr plus omega cross r. So we would be substituting the values in the similar expression, but before substituting these values, we want to have the acceleration which is derived from this expression. So in order to get the acceleration derived from this expression, we need to derivate this particular expression with respect to time. So the derivative is derivative of this vi with respect to time for the inertial frame of reference, that would be equal to d by dt. That means the derivative of this same quantity with respect to time, which is v of r plus omega cross r. So if I multiply or if I derivate this expression with respect to t, what do I get? I need to apply the product rule for it. So this would be this first function that would be constant for me. So what I can do, I can substitute this dvi by dt as acceleration, and the derivative of this is dvr by dt. For this I need to apply the product rule. So what is that? The derivative of this cross r would be the same, plus omega remains same, and the derivative of this would be dr by dt for the I frame of reference. So here what happens, I need to substitute this dv by dt value. So I have got this expression previously, which is dr by dt, which is dvr by dt. So I can substitute, or I can put in the value which is dvi by dt plus omega vr, and this values remains the same, which is d omega by dt cross r plus omega dr by dt for I. So this dvi by dt for r would be termed as acceleration for the rotating frame of reference. Omega cross vr remains the same, and this d omega by dt for I, it would also remain the same, and dr by dt is vi. Now if I consider that the earth is rotating with a constant angular velocity, so the derivative of this constant value would be 0. So I can replace this d omega by dt by 0. So ar would remain the same, omega into vr would remain the same, this would be 0 plus omega into vi. Now what happens, I need to substitute the value of vi in terms of the rotating frame of reference, so that everything comes in terms of the rotating frame of reference. So acceleration for the inertial frame of reference would be expressed in terms of the rotating frames of references. So ar would remain the same, omega into vr plus 0 plus omega, and this vi can be replaced in terms of vr plus omega cross r. Now I want to find out what is the force associated. So I need to multiply the entire equation with mass. So it becomes mass into ai, this becomes mass into acceleration for the rotating frame of reference, plus 2 times, because when I solve this expression I will get 2 times omega cross vr. So mass is multiplied there, and here also I will multiply the mass omega cross omega cross r. So what happens, I will get this final expression which is mar, that would be equal to mai minus 2m omega cross vr minus m omega cross r. So this would be the final expression that I was talking about in the initial part of the video, and this particular expression has certain components of the forces. This mass multiplied by the acceleration is termed as the force with this, which is due to the rotating frame of reference, m into ai, the force which is due to the inertial frame of reference. This particular value of the force, which is minus 2m omega cross vr, this is called as Coriolis force, and another expression which is minus m omega cross r, this is termed as the centrifugal force. So we will be discussing shortly these centrifugal forces and Coriolis forces. So what is the centrifugal force? Let's say I have a bowl, and in which I sprinkle some marbles, and I keep on rotating that bowl. So what happens to that marbles? The marbles would be stuck to the walls of those containers. That means it would be moving towards the wall, the marbles would be moving towards the wall of the container, and that particular force which is exerted to the marbles, that particular force is called as a centrifugal force. So here, if I talk about the definition is, it is the fictitious force which is acting on the particle which is at rest. So the particles are particularly at rest. That means Vr here would be 0, and the expression that I have already told, the expression is minus m omega cross r. Another is Coriolis force. That particular force is also termed as a fictitious force, and which is acted on the particle and that force is only exerted when the particle is there in the motion. That means Vr is there in the equation. That means the particle would be having some velocity, and that velocity is with respect to the rotating frame here. So the Coriolis force causes the moving particle in the northern hemisphere to deflect towards the right of its path. This we would be discussing, but this is due to the rotating motion of the earth. What happens to the particle, or the particle shifts towards the right or towards the left whenever we keep the particles or we make the particle fall from the earth's northern part or the earth's southern part. So explaining these concepts, let us consider that this is earth, and the earth is rotating at an angular velocity which is omega, and I place the object at the north. And I have already told you that this earth is moving with different magnitudes of forces, and that magnitude of the force increases. So if I throw the object from the northern pole, so what will happen? Because of the different magnitudes of the forces, it would be diverted towards the right of its path. And similarly for the southern hemisphere, it would be deflected towards the left of its path due to the changing values of the forces. So this is a relation, or this is the aspect which is related to the Coriolis force which is there in the rotational frame of references, particularly for the case of earth. So with this, we come to the end of the video, in which we learned about the inertial frame of references, the non-inertial frames of references. We have learned about the definition of the rotating frames of references, and also we have seen a derivation which is related to rotating frame of reference.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.